Can you hear the audio okay from the online students?
Yes.
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 So there we will continue and hopefully we will finish. So we're learning about properties of actually yes. We're learning properties of regular languages, and we are trying to identify if a particular language is regular or non-regular. What we discussed toward the end of the previous class. What we discussed toward the end of the previous class. Pumping lemma. Right? Before pumping lemma, did we finish the process for the pumping lemma? We haven't done the pumping lemma complete example from previous lectures. So then, before pumping lemma, what did we discuss? Pigeonhole principle, right? So the pigeonhole principle. I have this particular example. So we know how we can show a language is regular or non-regular using the pigeonhole principle, right? Suppose we have this language. The question is, can we apply the pigeonhole principle to show that this language is non-regular? Okay? So the next 5 minutes, trying to come up with strategy, a rough idea, how we can show that this language is non-regular using the pigeonhole principle, not the pumping lemma. It's best to try to write down strategy how to do it. It's not going to get it. So, excellent. For exam, you need to show it, not looking at it. right, so let's give everyone like 1 more minute. Show that this language is non-regular union. Transition. But before transition, what is the first thing we should do? Alright, what is the big picture? Prove by the contradiction. That's the first thing should come to your mind, right? So the only way to show a language is non-regular is using a contradiction. And how many ways that we could use a contradiction to show that the language is non-regular? Right. Before we get to that solution, let's think out loud how we can solve or how we show by contradiction that the language is non-regular. How many approaches? Two, right? Pigeonhole principle and the pumping lemma. Okay? So now here we can apply just one approach, the pigeonhole principle. So what does the principle tell us? Chris? So we get there in a minute. But what does the pigeonhole principle tell us? What is the principle? What is the basic observation?
There are too many states. There are more states than
Okay. So there's more states than transition. So now go back to the analogy of the pigeon and hole, right? So we have the finite number of holes, and we have some other number of n number of pigeons. And what is the condition for that to be the truth, to be the case? Well, the condition is that the number of pigeons has to be greater than the number of holes, right? And if that's the case, then when you put them into the corresponding hole, then at least one hole would have more than one pigeon, right? So now we're using that observation for this particular problem, okay? So now first thing we do here is we assume that by condition L is regular. If L is regular, then what?
Then we can make a DFA for it.
Okay, so then we can create a DFA. That can accept. Okay, so then that DFA will accept the language describing relationship. Okay, so now what? Do we need to construct a DFA? How come? Okay. So what is the problem properties of the DFA. Is it a finite machine or is it an infinite machine? It's a finite machine, right? So meaning that we have a fixed number, a set up stage. Okay. So now, if this machine is finite, then we're going to be using the definition of the transition function, right? To show that this language here would be non-regular, but then how do we, the thing is, how do we pick W to show by the transition function? What are some examples of W that we can use to show that the contradiction that's going to happen if we are assuming that M is regular? How do we pick W? Any idea? Okay, give me an example.
Like A.
This string. Okay. So in general, like what type of string? This is finite string, length 3. But we know that this language is
Like A
A to the N. Can we show that if my string A to the N, then my WW would be A to the N? A to the N is non-regular. Well, remember the example that we showed earlier, right? So we have the language A to the N, B to the N, right? And we're gonna decide to split this guy such that we have A to the N and A to the M, and somehow the transition would end up in the same state, Q, right? And here. In the previous example, we start from the initial state, and then we pick A to the N, that transition to some Q state, somewhere in that machine, okay? And then at the same time, we have A to the M is also ended up in the same state Q, right? We know that A, N and M have to be different, right? Based on the Pigeonhole Principle, right? So now, from here, we know that this language, this machine DFA, for example, for this case, would accept A to the N, B to the N, right? Because we assume that this language is regular, meaning that there's a DFA for it. Okay? So now, here we do the simple connection. Right? So now we can transition from Q, B to the N, and this would be the final state. Okay? And the consequence for this is that now this also transitions to the final state. Right? And because the machine accepts this, therefore the machine also accepts this string, A to the M, B to the N. And because N and M are not the same, this is a contradiction. Therefore, this language right here we showed earlier is not regular. Right? So now how do we use the same concept for this language, WW?
So would we have to create a string that would work in this language that should not work?
Exactly. We have to pick strategically a string W. That would allow us to show the contradiction. So what is W going to be? So earlier, one of the class members say pick A to the N. Would this be a correct string to show this is the non-regular language? If not the case, then WW would be A to the N and A to the N. Right? Okay, so how do we show by the transition function? How do we decide to split? And remember, there's also, this only works when you have the alphabet only one symbol A. Right? This language also be able to accept W's such that it's also can be. Right? So meaning that when we pick W, it's have to have both flavor. So this only show for one flavor. So what kind of W should we pick?
So should we show W that uses both A and B together, maybe?
For this language here, you have to pick both. This have the string W have to have both A and B in it. Simply just pick A to the N is not sufficient because it's only for the alphabet of just one symbol.
So should we say A to the N, B to the N?
So what if we pick A to the N and B to N or M?
M?
M, okay. A to the N. Okay. So now, suppose we pick this string, W is A to the N and B to the M. So now a language, that language L would be W dependent on W, meaning that we get this string. Okay, so that's how we gonna show by using the extended transition function. If it's too tough to show with this, using different string W. You don't have to using this W. Come up with new one.
You just do like a W, A, B there.
So A, B to the N. This string?
Yeah.
Okay. Now if you pick this, you're gonna have WW would be AB to the N and AB to the N. Right? So that have to be that string that accepted by that language L. Okay, now how do we decide the transition function for this string?
Delta star.
Okay? Do not
W. Or A, B to the N. Or A to the N.
AB to the N.
A to the N, B to the N.
Okay, so then we're gonna not going to use this case. What about the person that exists in this string? Are you going to construct a delta function to show the contradiction? We need to understand this concept before we bring on to more complicated languages. Otherwise, we don't have enough foundation. How do we pick W?
Does it have to be secular language or it doesn't?
Well, it have to be because that is the assumption. The assumption is relevant. The assumption there's a DFA for it.
I was just using the first one.
No. Meaning what? Meaning that you split this in half. Because again, we have the same WW, right?
And W is equal to A to the N, and W is also B.
No, you cannot have both, right? Because if that's the case, if W just simply A to the N, then WW would be A to the N, A to the N. Okay. Likewise, if you take W is B to the N, then WW would be B to the N and B to the N. Right? And again, each of this is of W here would be just a partial of that language. We need to show that the inclusive, and all we need to do is just pick one string to show that this is not regular. Only one string. There's multiple strings that we can pick, but only one string.
Can't you just pick A, B? W is equal to A to the N, B to the N.
This one? Okay, so if you pick this with this, that's fine. So now, then we have to write out WW would be this way, right? A to the N, B to the, I mean, if we pick N here, and that would be N, that would be N. Right? So now, if we pick this, how do we show by the traditional function?
You subtract the delta star Q naught AB equal to QI.
AB, A to the N,
Well, A to the N, B to the N,
A2,
N,
okay,
B to N, or
B to the N,
equal to QI.
okay, some Q. Okay, now what?
We need to do another transition with N instead.
Okay,
Same thing, but instead of N, it's
okay,
also equal to Q.
equal to Q. Very good. Now you can see that this is the concept of the pigeonhole principle, right? Okay, now how do we make the final transition to the final state of this machine, which allows you to draw the contradiction observation.
And is
Okay, so M, and there's another set, right? Then what? No, I mean, you want to continue with this or? All right, then go ahead.
AB, just AB, not AB.
You're saying that just the first part, the first part. Okay. Yeah, go ahead.
On this question, isn't it basically the same thing? Like, it doesn't matter how long the string is, as long as it's a string. So, like, you said we don't have the AB, AB, but if it's AB, AB, or just AB, or AB, 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 doesn't matter because we're just looking for any string in W.
Any string in L, that will be any the same thing. First,
How is this any different than our like A to the end? It feels like you're just
well, the thing is, I'm following the suggestion from the student.
yeah.
I'm not saying that this is correct selection of W. Just walking through to the path, seeing that the pigeonhole. So you said, so Chris say that, isn't it, if you pick this guy, W is A to the N, B to the N, isn't it the same thing that we did earlier, example? And if that's the case, then how do you show using the traditional function?
Okay. So for this one, you do I definitely keep those two up, and then you say from there, Q star A to the N equals QF.
Okay, so keep these two.
A to the N, B to the N equals QF.
Okay, so you're saying that now,
From either of those.
so from Q,
From Q, yeah.
right, you're processing A to the N, B to the N, go to the final state, QF.
Yeah.
So if this is the case, then this guy will transition here, this guy will transition here.
Yeah.
Right? Because we know that N and M, they are not the same. Okay? So then if this guy, this machine M, accepting this guy, it should also accepting this guy, M, right? But because N and M are not the same, there's contradiction.
Yeah.
Right?
How do you prove this? Like, how do you show this?
Right here.
Yeah, because W, it shows that they're different
Well,
values.
so what we say here is that, so this string right here would be in that language, right?
Yeah. Oh,
And the consequence for this is that you have another WW, A to the M, B to the M, A to the N, B to the N. This has to be in this language on this machine. It should be accepted by that machine name.
yeah.
It's not. Therefore, there's a contradiction. Here we can conclude that L is non-regular. Okay. Does it make sense? Okay. Again, you have to use in this string. No. There's other string. Another easy one would be W is A to the N, B. Alright, so if you take, so this one, it's fine. Okay, answer. To show by the Pigeonhole principle. Right? But we can make easier argument if we use this one. Right? So now the same concept with W would be A to the N, B to the A to the N, B. Right? So now we split this in half and show this first part right here would end up in the same Q state. Okay? And then simply just one transition from that to the final state. Okay? Any question?
What would you write? What would you write after you get to, showing that WW equals A to the M, B to the N, A to the N, B to the N, not part of L? What would you do there?
Well, you say that since N and M are not the same,
Yeah.
and because this guy right here is indeed in that language.
Yeah.
But this guy, because of the assumption that the machine should accept this guy, therefore should accept this guy based on the transition function here, right? And we know that this is not the case.
Yeah.
Therefore, we say this is a contradiction.
Yeah.
Does that make sense? Any question? So then again, you have two examples for the Pigeonhole Principle. Right? We're going to move on to finish the pumping lemma. Okay. Any question about the Pigeonhole Principle? All right, so pumping lemma, right? So we call the definition of a pumping lemma or the theory, right? So we're going to use the same language here. Okay? So you can see the differences between the Pigeonhole Principle and the pumping lemma. So now, what do we know? How do we prove the pumping lemma? What is the first thing we should do?
Create an infinitely long language.
Creating an infinitely long language. Okay, what is that language?
You can just say, I guess using like the previous one, a to the n.
Okay, so W would be A2. What is W? Because the first thing we should do is we are assuming that L is regular, right? So the pumping lemma and the Pigeonhole Principle using the same concept. Assume that it's regular. Okay? So now, first thing is we assume that it's regular, right? Then we can use the pumping lemma. Without the very first assumption, whatever you write after that would be incorrect. Okay? Assume that the language is regular. Okay? And the condition here is that when we're using a pumping lemma or Pigeonhole Principle, right? We have to know that the language is infinite regular, not just finite regular languages. Okay? So if that's the case, then we can use the pumping lemma. Okay? So what it is say that we can pick some value m, right? And that value m is given by the lemma. So if we pick w to be the same that I showed earlier, a to the m v or a to the n v, doesn't matter, right? But here, if I pick m there, that would be this w. Okay, again, when you're solving these type of problems, you have to think of string w. That you know from the beginning that it's going to give us the contradiction at the end. Okay, you have to pick the w string or whatever, and set the string in that language carefully. Okay, so now we know this. Then WW would be a to the MV, a to the MV. Right? Then what? Let me see. I have a book with me. All right. So we All right, page 118. Okay. So is this in L? This is a member of L. Yes.
Yes.
Right. Say that W has to be in L. Okay. What else? The length of W has to be C. What is C? Not constant. Case 118. Theorem 4.8. Okay, we know that yes, this guy is a member of the language L. Okay. And what else? Width is what? The length of this guy has to be what? Greater or equal to? To what?
One.
1? Where do you say equal to 1 in the theorem 4.8? M. Exactly. Right? We pick M. Right? Must be M. Okay? Is this string here, the length is greater or equal to M? Some nodding to your head. Okay, what is exactly is W length again? 2M plus 2. Check. This guy? Check. Okay, now what? What we can do next? Okay. It's okay to be wrong. We all learning. Now what? Well, now we say that W can be broken down into X, Y, Z. This guy, right? Can be broken down to X, Y, and Z. Right? Exactly. Okay. To satisfy that, what is X, Y? The length of X and Y would be less than or equal to M. And The length of y is this. We know that because of pumping lemma, we can break it down to x, y, z. So then what is x, what is y, what is z corresponding to these input? Such that it's going to satisfy these two conditions.
I think I think that's first X, Y. I like X, Y.
Oh, it says right here, the lemma. The lemma saying that the length of x, y less than equal to m. Okay, now here's a point where we have to think. Problem solving. We have collected the 1, 2, 3, 4, 5, 6 in class and 12 in online class. We should be able to come up with x, y, and z, break it down using these input to satisfy these two conditions. How do we break it? Problem solving.
So y equal to a to the m?
Y equal to a to the m. Okay. How about x and z?
Or like,
No, we're not pumping yet. We're just picking x, y, and z of this string. We haven't yet to the point where we need to pump it yet.
X equals lambda.
X equal lambda. Okay. What about z?
Equals the rest of the string. So b a to the m b.
B a m b. Okay. So if we decide to break it into this way, okay. Now go back here. X concatenated with y have to be less than or equal to m. Is it? Does it meet this condition? If we pick x, y, z like this, like these. Now check. X, y, not to less than m.
what is M again?
M is just any number. Right? What is m? M is some big number, some small number. Could be 1, could be 10, could be 100, could be million, it doesn't matter. It's just m. This is number. Okay? So we meet this condition, right? Because looking at the length of this guy, this is m. Is greater than, less than m. Is it? What is a to the m? What is the length of a to the m? Is this number less than or equal to this number? Okay. What about this guy? The length of y is greater than 1. It's greater than 1. Good. Okay. So now, if we decide to pick this guy, now we can write wi. I'm going to erase the top form. Okay. Would be what? Would be x, y, I, z. Right? Would be lambda a to the I. Z would be b a and b. Right? This is what we decided earlier. Right? And I can be 1, 2, 0, 1, 2, 3, and blah, blah, blah. Right? Okay, now we're going to pump. So you're saying that I can be any number, right? So now if I pump I to be 2m, can I do this? Can I pick I to be 2m? Well, let me rate this guy. Okay, we're going to be good with this point. Let me rate this guy. So if I 2m, then what? And W will be lambda A 2m, B A M B. You with me? Any question? So what's wrong with this string? What's wrong with this?
Well, the A's need to have an equal length, whereas in this string, the first A has a different length than the second A, which means that's not in the language.
Exactly. So again, I can you don't have to think about this. This is lambda, right? So look at this W, W, and this W, W, right? So we know this is in that language because by pumping lambda function. Okay? But we say that if that's the case, you can pump I to be any number. Okay, if that's the case, I'm going to pick I equal to m, and you can see here that indeed this is not the same as this guy. So here's a contradiction. Okay. If we have a contradiction here, then what do we say?
It's irregular.
It's non-regular. Okay. Any question? So now go back to this example that you did for the pigeonhole. Show that this is non-regular using a pumping lemma. So right now it is 11:59. So let's take 5 minutes. So 4. Okay, so anyone would like to get us started?
Okay, so
Okay.
for pumping lemma for this, you need to have x equal to lambda, y equal a to the n, and z equal b to the n.
Wait, x is lambda, y is,
A to the n,
okay,
and b would be z to the, no, z is b to the n. Okay, and then when you which would make x y z equal to lambda a to the n b to the n. And then if we do x y y z, it would be lambda a to the 2n b to the n, which is not in the language, making this an irregular language.
okay. So this is the rather a shortcut to get here, right? But in your homework answer, in your exam answer, you have to follow through the systematic that we did before. So this is correct. Okay, at the end, this is what you need to show. So what is the first thing? You assume that L, go ahead.
Assume that L is regular.
Very good.
String W equals A to the M, B to the M is an L.
Very good. And then before that, we have to assume that let M be
Yeah, let M be.
the pumping length result from the pumping lemma. Okay, now let U be A to the M, B to the M. Good.
And for any choice of y, since the length of x and y are less than or equal to m, any choice of y will equal a to the k. K is greater than or equal to 1 and less than or equal to m.
Very good.
And so now if you choose I equal to 2, then a new string will be created, which is a to the m plus k, b to the m. And m plus k is not equal to, m plus k is greater than m, so the string is not an L. And this is operation, so L will not.
Exactly. Okay. So by the time we do it, we get here, right? This is the pumping here. This is the pumping leg of 2. Right? So here, pumping leg of 1, which we get the same string, which is in L, but we need to pump it one more Y. And this obviously is not in L. If you come to 3 and 4 and 5, it doesn't matter. You're going to see the same contradiction happening. Okay. Any question about pumping lemma? Again, once you understand it, it's pretty straightforward. It's just a matter of how we break down X, Y, and Z. Okay. All right, if no question, then we're moving on to the next chapter. Context-free language. Okay. So do we know at this point how to identify regular languages, how to construct or prove that either language is regular? We know that some languages are not regular. And one way that we can show it's not regular is using the Pigeonhole Principle or the pumping lemma. All right. So now, next we're going to explore a new class of languages. And that new class would be context-free grammar. Before we start, anyone have an idea what is context-free grammar? I mean languages? why would we be interested in context-free languages? Anyone heard this before? Anyone heard of Noam Chomsky? Noam Chomsky. Who is Noam Chomsky?
He was an author.
He's the author. What else? He's also a professor. He's also the person that formalized a class of context-free languages. Okay. So what is the purpose of the context-free languages? Okay. So here in this chapter, we're gonna identify whether a particular grammar is context-free. So again, when we talk about grammar, we talk about language, are they the same? What is the relationship between language and grammar? What about regular expression? Right? So if you recall from regular expression, regular languages and regular grammar, right? They're all connected through the finite automaton, right? So now here, in order for us to understand the context-free languages, we're going to be using a new grammar, okay? And we're going to discuss the connection or the relationship between regular languages and context-free languages. Okay? We are going to construct context-free grammars for simple languages. We're going to produce the leftmost and the rightmost derivation of a string generated by a context-free grammar. Show that a context-free grammar is ambiguous. What does it mean if a grammar is ambiguous? And we're going to show how to rewrite a programmer to remove the ambiguity. Okay? So definition. A context-free grammar is a grammar G with all the production have the form A to X, where A is a member of B and X is a member of B union P to the star closure. Okay, so take a moment, look at this grammar, and we say this is a context free. How does it differ from regular grammar?
Less rules?
Less rules. So what does it mean if you have a regular grammar?
Well, regular grammars have initial and final state.
So regular grammar means that you have the initial and final state. Anyone else? Any idea? What does it mean if you have a regular grammar? Okay.
It's either left or right linear.
Exactly. It's the left or right linear. In what?
As to a.
In the production rules, right? So everything is the same except in the production rules. Okay? So for the regular grammar, if G is regular, what is the definition? CSP. And where or so which one is left linear, which one is right linear?
The first one's
Which one?
the first one is left.
How do you know? Well, you get it right. Just asking a little bit hard, a little bit to see your thought process. How do you know that the first one is the left linear? Because the production rule on the left, which left?
The left linear. The first
Well, right here is the context-free grammar. Right here is regular grammar. So when you compare these three, how do you know that this is the left linear, this is the right linear? Nick?
The first one, the B is the left here. Bottom one, the B is the right here.
This guy. What is B?
Non-terminal symbol.
Non-terminal symbol. And which set does B belong to? B. Okay. A regular grammar is a left or right, and it's at this form. A context-free grammars, this is the form. Okay. Any question about the distinction between the regular and the context-free grammar? That's so simple. That's all you need to know. Okay? So now we say that a language L is said to be a context-free if and only if there's a context-free grammar G, such that the language is recognized by the language, by the grammar that represents that language. Okay? But if you recall, this is the definition of regular grammar, right? So it turns out that later on, you're going to see many useful languages are not regular. Okay? We're not saying that the regular languages are not useful, but to extend the power of a set of language, right? The context would give us extra tools. Context-free grammar would give us, would do that for us. Okay? And the context-free grammars are very useful for defining and processing of programming languages. Okay? Which you're going to learn in 370, the concept of programming languages. Right? You're going to learn that Java, you're going to learn that C++, you're going to learn that Python. When you build a compiler, that compiler has to process a set of production rules so that if you hit x equal y on the statement assignment for your programming language of choice, then the computer would be able to generate the correct input, meaning that we translate the high-level languages, which we can type, to the main machine languages, which only 0 and 1 that the computer can process and understand. Okay? And the context-free grammar, as you discussed earlier, there's no restriction on the right side of its production. Okay, while the left side must be single variable. What is the left side here? Which one are we talking about? So if I'm going to add much more, so these are the regular languages. And if I have a context-free, then this is the only difference, right? So which one is the left, which one is the right? And how do we pick the reference point based on the production rule to tell? What does it mean here? Am I confusing?
You can't tell if it's left or right linear.
So pick this one, for example. Which one is the left side? Which one is the right side?
A is the left side and BX is the right side.
And this is the right side. Okay, and how do you know? This guy right here is your reference, your point of reference. This is the guy here telling you whether it's a left or right. Left, right. Okay, saying that the right side is production, there's no restriction. Okay, any x. But the left side has to be a single variable. Okay, any question? Okay, now it turned out that regular grammar are context free. And the family of regular languages is a proper subset of the family of context free languages. What does it mean?
Means the regular languages are also context free.
Exactly. Okay. See, this guy right here is also a production rule with this guy. All right. It's just that you have to restrict either left linear or right linear. And this guy, this can be anything. So now what would be it? So if it's the linear, left linear or right linear, and this is the proper subset of this guy, right? So then we're going to see that there's also non-linear grammar. Okay? So now if I draw a Venn diagram, Okay, we recall from so let's say this is the class of regular languages, right? So then what's happening here? You have L is regular. What else? What did we show earlier? What is this? The homomorphism, right? This is also regular. Right? So everything here is regular. Okay? So context free is a little bit out of here. Okay? Context free languages. All right? So the question then is, if I have this guy, we know this is not regular. Does it belong to this guy? Okay. And is there anything else outside this layer? Is there anything outside this layer? So we know this is very powerful, right? It's even more powerful than this guy. What about this guy? Okay, what about this guy? Okay, we're gonna, let's see. All right, so I'm gonna stop here. Okay, next class, we will discuss the context tree, and hopefully toward the end, we're gonna cover the more sophisticated languages out there. Okay? So if you haven't done reading chapter 5, please do. I'll see you on Monday. And please work on, actually your homework 7 has been posted. And I intentionally put the deadline next Monday, the Monday after you turn in your outline. So please work on your outline. If you have any questions, feel free to email me. And I'll see you on Monday.
Bye. Thank you,
So-
Professor Boyd.
Bye.
Bye.
Yes, Professor. See you on Monday.
Bye. See you.
Have a great weekend.
Bye. You too.